a carpenter is holding a 12-pound, so please note this is a U.S. problem, so that is a weight. That would mean that the weight of the board mg is equal to 12 pound. But it's a 2x4 as shown. We're also told that he exerts vertical forces on the board at A and B really, and we just want to determine the forces at A and B. So we're going to want to draw a free body diagram where we isolate the board. So if you just imagine that we draw like an envelope around it, and then we want to remove the board from everything that's touching it, and then replace everything that's touching it, and this would include action at a distance objects such as the Earth, by the appropriate force representation. So we're going to have to remove his hand at A, so there'll be some kind of a vertical force here. We could draw it up, we could draw it down, it wouldn't matter. And then we're going to have to remove a hand at B, so there'll be some kind of a force here. We'll either draw it up or down, it doesn't matter. And then we'll have to put the weight of the board on, and this is to be considered a uniform object. So it's 2 plus 6 feet makes 8 feet long. So right in the middle, 4 feet from either end, we're going to have the weight, and the weight will be straight down. Now, to save time, I have already sketched this free body diagram, and here it is. So you can see I've got a normal force at A, and I have a normal force at B, and then I've got my weight component as well. Now, I have selected downward for my normal at A. I could have selected upward, and I've selected upward for my normal force at B. Again, I could have selected downward, and then I have the weight. Notice I've put the weight right in the middle of the board, 8 feet long, so 4 feet from either edge. For my coordinate system, I have selected X to the right and Y up and counterclockwise positive. We have pertinent dimensions, we have our labels on. G is the mass center. Again, remember that mg is equal to 12 pound. And once you have the free body diagram, the problem is really essentially over. We want the forces at A and B. So, forces in the X will not do anything for us on this problem. We could write forces in the Y equals 0. So I have NB assumed positive. I drew it up, and I called up positive, so I'll put it as positive. And then I have minus NA and minus MG, and that would be 0. Again, I assumed NA down, and I drew MG down, so that's negative with my choice. And then I could take some of the moments. We could do any point we want. Let's start off with some of the moments around B is equal to 0. So we called counterclockwise positive. So the normal at A is going to make a positive moment around B through a 2-foot moment arm. So we have 2 times NA. And then MG happens to also be 2 feet away from point B, but it's on the opposite side. So it's going to produce a clockwise moment, and that would be equal to 0. And it's easy to see at this point the 2's would cancel, and it happens to be the case that NA is equal to the weight, which is in fact 12 pounds. And we get a positive value for this number. If we take the mg term to the other side, it would be positive, which means that NA does in fact point downward. When you are working equations in equilibrium, often a person will not know if they should draw a force up or down, or right or left. And in mechanics, for many cases, it doesn't matter. This is one of those cases. If we had assumed that the normal at A was upward, what we would have found is that we would have gotten a negative sign, algebraic, S-I-G-N, on this number. And the negative sign would mean that our direction was incorrect, and the force was actually directed in the opposite of what we selected. It's not a big deal, though. A person just needs to remember that mechanics is a wonderful subject, and that it will let you do that. Okay, now that you have NA, you could substitute it back into your first equation, and you would have that the normal at B is equal to NA plus MG, so that you would find that NB is actually 24 pounds, and it's actually pointing up, because again, you would get a positive sign for this reaction, and that would mean your direction was correct. Now, you didn't have to write these two equations. You could also have written some of the moments around A is equal to 0, in which case you have 2 times NB. That's going to produce a counterclockwise moment, and then minus 4 times MG is equal to 0. which you can see that NB is equal to 2 times the weight, which is 24 pounds. So any number of ways to solve it. These are probably the two that would be the most used. And we don't have to use some of the forces in the y, but we certainly can. Again, this is a nice category of problem because all the reactions are pointing either up or down. All right, that's it.